Good evening, everyone. Okay, settle down first. So we'll get started. Those are online. Am I audible?
Yes, sir.
Okay. Yes. So the first question that we are going to solve based on motional EMF is right. So the first question that we are going to solve based on motional EMF is an aircraft with a wingspan of 40 meter, right, flies with a speed of 1080 kilometer per hour in the eastward direction at a constant altitude in the northern hemisphere, where the vertical component of the Earth's magnetic field is given as 1.75 into 10 power minus 5 Tesla. Find the EMF that develops between the tips of its wings. Okay. If you observe, the length of the wing is going to be 40 meter, right? The speed is considered to be 1080 kmph, or this is 1080 into 5 divided by 18. So when you solve this, 18 will cancel this 60 times. So 60 into 5 is going to be 300 meter per second. And it is moving at a constant altitude where the vertical component of the Earth's magnetic field is how much? So vertical component is represented with the symbol B and a subscript B. Okay. So BV is equal to 1.75 into 10 power minus 5 Tesla. Find the EMF that gets developed across the ends of this wing. So we know that the formula for EMF is going to be B into L into V. The value of B here is 1.75 into 10 power minus 5 into length is going to be 40 into the speed is going to be 300, right? So 1.75 can be written as 7 by 4. So 7 by 4 into 10 power minus 5 into 10 power 3. It is 10 power minus 2 into 4 into 3. So 4 and 4 will get cancelled. 7 into 3 is going to be 21. So 21 into 10 power minus 2 volt, or it is going to be 0.21 volt. So this will be the EMF that is getting induced across the ends of the wing. Okay. So you need not copy the question. Okay. So I'll make sure that you get this file. Can actually come front. Just see that it's not hit. Done? Shall I proceed? So now the second question is, a jet plane is traveling west at 450 meters per second. So speed is given as 450 meters per second. If the horizontal component of the Earth's magnetic field at that place, so if the horizontal component of the Earth's magnetic field at that place is given as 4 into 10 power minus 4 Tesla, and the angle of dip, okay, so the angle of dip is given as 30 degrees. Find the EMF induced between the ends of the wings having a span of 30 meters. So length of the wings is going to be 30 meters. If you observe, this problem is similar to the previous one, except the fact that there they gave the vertical component of velocity. Here they have given you the horizontal component of velocity. So for you to find out what is going to be the motional EMF, all that we need is the vertical component of velocity. Because it is going to, the plane is going to go in this direction. You need a velocity, you need a magnetic field. 1 minute. Correction. So in the previous problem, they gave you the vertical component of magnetic field. Here they have given you the horizontal component, but what have they given in addition? They have given you something called as angle of dip. So for you to find the motional EMF, you need the vertical component of magnetic field, because vertical component will be perpendicular to this. So that's what the motional EMF told, right? The conductor is supposed to move perpendicular to the magnetic field, right? So when BH and delta is given, there is a relation between BH, delta and BV. So first of all, you need to understand what this angle of dip is. So whenever you place a compass in a magnetic field, right, the compass is going to rotate like this to show the north and the south direction. But along with the rotation, it will also oscillate like this, right? So what is happening is it is getting dipped, right? So this bend that is taking place when it is rotating is what is called as the dip. Means it is making some angle with respect to the magnetic field is making an angle with respect to the horizontal. Meaning, if the magnetic field due to the Earth at a particular location is in this direction, then this magnetic field due to the Earth can be resolved into two components as BH and BV. Okay. So the Earth's magnetic field at a place can be resolved into two components as BH and BV, where the angle made by the Earth's magnetic field with the horizontal is what is called as angle of dip. So this is what is called as angle of dip, right? So if you know BV and BH, the relation between angle of dip and the vertical and the horizontal component of magnetic field is given as tan delta is equal to BV divided by BH. The reason is very simple. Both are vectors. With respect to delta, this is the opposite, this is the adjacent. Okay, it is going to be BV divided by BH. So what is the value of BV? That is what we need to find. What is the value of BH that they have given already? It is 4 into 10 power minus 3. Sorry, 10 power minus 4. This value should be equal to tan delta. Tan of delta is how much? Tan 30 degrees. So tan 30 is going to be 1 divided by root 3. So what is going to be the vertical component? It will be 4 divided by root 3 into 10 power minus 4 Tesla. So 4 divided by root 3 into 10 power minus 4 Tesla. Now we need the value of EMF. So EMF is equal to B into L into V. I need to take the vertical component and plug it here. So this is going to be 4 divided by root 3 into 10 power minus 4 multiplied with length is how much? 30 into what is the value of speed? It is 450, right? So if you observe, this 30 can be written as 3 into 10. Can I do that? So when I write it as 3 into 10, I can say that this root 3 will cancel this 3 root 3 times, right? So 4 into 450 is going to give us how much? So 500 into 4 is 2000. From 2000, you remove 200. So 1800, right? So 1800 root 3. So 1800 root 3 into 10 power minus 4 into 10 should be the value of EMF that is getting induced. So this can be written as 1.8 root 3 into 1234 into 10 power minus 4 into 10 power 4. They both will get cancelled. So 1.8 into root 3 volt should be the answer. Is the point clear? So let me check the answer once. Can make a note of it. Clear? Should I proceed? Try this. I still copying. Solved it? Listen. Running north to south has rails which are 1 meter apart. So the distance between the rails is 1 meter, right? Calculate the value of the induced EMF between the rails when a train passes at a speed of 90 kilometer per hour. The speed of the train is going to be 90 kilometer per hour. This can be written as 90 into 5 divided by 18, right? So this 18 is going to cancel this 90 5 times. So it is going to be 25 meter per second. Again, if you observe in this problem, the horizontal component of the Earth's magnetic field at that place, the horizontal component of the Earth's magnetic field at that place is given as 0.3 into 10 power minus 4. It is given as Weber per meter. It's actually Weber per meter square. Okay, basically it is 0.3 into 10 power minus 4. Weber per meter square is nothing but Tesla itself, right? And the angle of dip is given as 60 degrees. So angle of dip is given as 60 degrees. Okay. Now, if you observe, the EMF is equal to B into L into V. So what is the value of B? B is going to be equal to, this is the vertical component of magnetic field. So we know that the vertical component of magnetic field divided by the horizontal component is equal to tan delta. So B vertical should be equal to BH times tan delta, right? So B vertical is equal to BH times tan delta into length into speed. So what is BH? It is going to be 0.3 into 10 power minus 4 into tan delta is how much? Tan 60, which is going to be root 3 into what is going to be the length? Length is 1 meter and speed is going to be 25 meter per second. So 0.3 into or 0.3 into 25 is going to give us 7.5. So it will be 7.5 into 7.5. It will be 7.5 root 3 into 10 power minus 4 volt. So this should be the answer. Okay. So those who are online are able to understand?
Yes, sir.
Yes, sir.
Yeah. What is the answer? So in this question, there is a conductor of length 1 meter and it is falling freely under the influence of gravity, right? It is falling down. So its velocity is in the downward direction. And it is falling through a distance of 10 meter. So that it cuts the lines of force of the horizontal component of the Earth's magnetic field. In this case, what is happening is the Earth's magnetic field is horizontal, but the velocity of the object is perpendicular. So unlike the previous cases, here we don't need the vertical component of magnetic field, rather we need the horizontal component of magnetic field. Okay, so for which I will take BH as it is. So BH is how much? 3 into 10 power minus 5 Weber per meter square, which is Tesla. We need to find the EMF that is induced in it. So E is equal to B into L into V. So here B is going to be 3 into 10 power minus 5 only, right? Length is going to be 1 meter, but we don't know the velocity. Since the object is traveling downwards under the influence of gravity, its speed is going to be root 2gh, because we'll apply the formula v square minus u square is equal to 2as. The object is initially dropped, u is 0. So when you take u to be 0, v square is equal to 2 into acceleration due to gravity is g, and the displacement is h. So v is equal to root 2gh. So when you apply this, you will get 3 into 10 power minus 5 into 1 is 1 only. So root of 2 into g value, take it as 10, and h also take it as 10. 10 into 10 is going to be 100. So square root of 100 is 10. So it will be 3 into 10 power minus 4, because 10 power minus 5 into 10 will give you 10 power minus 4, and you have a square root of 2 inside. So it will be 3 root 2 into 10 power minus 4 volt. So 3 root 2 into 10 power minus 4 volt is the answer. Done? So all of the problems are similar. We can do one last problem and then we'll move on to the next concept. So try this out. Try that. It is actually a derivation, the derivation we learned yesterday. Only difference is there they didn't give you any 5 ohm resistance. Here there is a 5 ohm resistor, that's it. Answer. So this question is, a conducting rod PQ in contact with metal rails RP and SQ, which are 25 centimeter apart in uniform magnetic field of flux density 0.4 Tesla, which is acting perpendicular to the plane of the paper. So if you observe, the magnetic field is going to be equal to 0.4 Tesla and it is going to be into the plane. Second, the length of this conductor is taken to be 25 centimeters, so 25 into 10 power minus 2 meter, right? Now, there is a resistance of 5 ohm that is connected between the points R and S, right? What is the EMF when the rod moves to the right with a velocity of 5 meter per second? So the rod is moving to the right with a speed of 5 meter per second. What is going to be the EMF induced in it? So EMF is equal to B into L into V. So B is 0.4 into length is 25 into 10 power minus 2 into what is the speed with which it is moving? It is moving with the speed of 5. So 25 into 0.4. So 25 into 4 is actually 100. 25 into 0.4 should be 10. So 10 into 5 is going to be 50. So 50 into 10 power minus 2 is going to give us 0.5 volt. So it is 0.5 volt. Now, what is the EMF when the rod moves to the right with a velocity of 5 meter per second? What is the magnitude and direction of the current through the 5 ohm resistance? So I is equal to E divided by R. So E is going to be 0.5 divided by R is going to be 5, which is going to give you 0.1 ampere. Am I right? So the current flowing through this resistor is 0.1 ampere. But the question is, what is the direction in which it is going to flow? So how do you do that? You need to use a Fleming's right hand rule. You can use that. So when you use a Fleming's right hand rule, first thing, extend your forefinger in the direction of field, right? And extend your thumb in the direction of its motion. And extend the central finger. So it is telling it is in the upward direction. So it is going to be from S to R. Is that what is happening? Field, this is the motion of the conductor, and this is going to be the direction of the current. So S to R is going to be the direction of current. Okay, let's validate it using the other logic also. I doubt S to R is the direction, but let's check this. See, this is there. So since the field is received by this sheet, what pole is it acting as? This is acting like the south pole. If this is the south pole, we are going to be the north pole. So when we are the north pole and the flux is increasing, what pole should get generated? South. So the current is supposed to be in the clockwise direction. So it is still going to be from S to R. So they have asked that thing only, no? Direction of current through the 5 ohm resistance, direction of current is going to be from S to R. Right? It is going to be in the clockwise direction. If the rod moves to the left with the same speed, what will be the new current and its direction? So if the rod moves to the left with the same speed, the value of current is still going to be the same. The value of current is still going to be the same, which is 0.1 which will be 0.1 ampere. But this time the direction of current will be reversed. It will be from R to S. So this is what is supposed to happen. Clear? Shall I proceed? Right. So I'll proceed to the next concept. Those who are online, are you able to understand?
Yes, sir.
I told you about, see the next problem, if you remember, I told you yesterday itself. I asked you to remember also half dl square omega, which is a motional EMF and the conductor is rotating. So you can remember it like a formula. There is one problem in your NCERT exercise where they will ask you, where they have a question based on this formula. Okay. Right. Now, we'll go to the next concept, that is now we'll discuss the next concept, which is self-induction. Okay. So till now we understood how electromagnetic induction is going to work. Right. So for electromagnetic induction to be produced or EMF to get induced in a particular circuit, what is a necessary parameter? The magnetic flux should change. Am I right? So if there is a change in magnetic flux, what can you say? There is an EMF induced. And that process is what is called as induction, or you call it as electromagnetic induction. So if you see in electromagnetic induction itself, now we are going to categorize them as two more types, as self and mutual induction, of which the first topic is going to be self-induction. Okay. So listen to this carefully. If I take this device, right? If I take this device where there are two coils, right? These coils have n number of windings around it. I'm not going to count them, but yeah, we have two coils where one of the coils is connected to a switch and the other coil, right? And the switch is connected to the battery. Okay. So this coil is connected to the switch and battery is the one which is supplying the necessary energy to this device. And the other one is not connected to any of the electrical sources. It is only connected to a passive element, which is an LED. So what should happen is, see, tell me one thing logically, had this bulb been direct, what should have happened? The bulb should glow. But now what is the scenario? The bulb is not directly connected to the switch, rather it is connected to the coil, and this coil is related coil. This coil, remember, this is the second coil is not connected to this coil and generate electricity here. So when I press this, what is supposed to happen is it should glow. Right? Are you able to see? But it will glow only till the time I press it. Immediately after I release also, it will glow. But it is not glowing continuously because it is happening only for a particular instance. So this kind of inducing EMF by producing current in one coil and an EMF in other coil is what is called as mutual induction. But if you see, the topic is not mutual induction, it is self-induction. So as the name suggests, right? Mutual means you need to have two coils in picture. So they should be coupled together. So that one is connected to the power source, the other is connected to the LED or some galvanometer, something. Now, assume that this coil is not existing at all. If this coil is not existing, then what will happen is, if I press the switch, there is going to be a change in flux taking place in this coil. So if the change in flux is taking place through the coil, which is directly connected to the power source itself, and if that change in flux through the coil is able to produce EMF in itself, what is happening? When you press the switch, there is a change in flux taking place in this coil, and there is an EMF getting induced in the same coil due to the change in flux. If this kind of a process happens, then that phenomenon is what is called as self-induction. So what is going to happen here is, when you talk about mutual induction, you need to have one coil that is connected to the other coil. So in one coil, there will be a change in flux taking place. In the other coil, there will be an EMF induced. That is mutual. But if within the same coil, you have the change in flux taking place and the EMF induced, that process is what you call it as self-induction, right? Now, let's try to understand why is this even happening, right? So this is the coil which I told you. This is a coil, and this coil is connected to the, so forget about the second one, this coil, right? This coil is connected to a closing switch and a battery, right? Now what has happened? Now the switch is open, right? Switch is open means the battery is not connected. So when I have this kind of a scenario, listen to the process. Initially, when the switch is open, right? I'm going to write down the sequence. Tell me what will happen when the switch is open, right? What is going to be the amount of current that is flowing through the circuit? I is 0. So when I is 0, is there any magnetic field that is induced in this coil? No. So when I is 0, can I conclude that the magnetic field is also 0? So when the magnetic field is 0, since there is only one coil which is generating the magnetic field, that is the one which will produce the necessary flux also. So flux is also 0, right? So all this is happening when the switch is open. Let me call that instance as t is equal to 0, because for me to induce EMF, I need to have a change in flux taking place with respect to time. So for me, time is a very, very important parameter. That is why I'm having my time also getting recorded. So t is equal to 0. This is the scenario. This is my observation. Are you in agreement with this? Now the question is, when I close the switch, right, since you're using a DC battery here, first current was 0, then the current will start growing from 0 to some steady state value, right? So let's say a t is equal to some time t itself, okay, at random time t. After the switch is closed, right? After the switch is closed, current becomes steady. When current becomes steady, can I conclude that magnetic field is going to be steady? When magnetic field is going to be steady, can I conclude that the flux is also going to be steady? Means it's going to be a constant value. It is going to be constant. But the whole process of the EMF getting induced in this coil should take place between this t is equal to 0 and t is equal to some time t. So during this process, what will happen is there will be some growth in current taking place. Means from initial current being 0 before the switch closed to raising to a steady state value, there is going to be a slight growth in the value of the current, right? So during the growth of current, right? During the growth of current in between these two processes, can I say that when the current grows, the magnetic field associated with this coil also grows? When magnetic field associated with the coil grows, can I say flux also grows? So whether flux is going to grow or decrease, there is a change in flux. So this change in flux is taking place in the intermediate process between t is equal to 0 and t, right? And due to this change in flux, what will happen is there will be an EMF induced in this coil, which will try to oppose the cause according to Lenz's law. So that's what Lenz's law says. No, EMF will get induced according to Faraday's law, but that EMF should oppose the cause according to Lenz's law. These are the two facts we know. Now the question is, I need to understand in which direction will the induced current get generated. I'm talking only about the first scenario, okay? I'm talking only about the first scenario. So what is happening when you close the switch? Tell me the sequence. When you close the switch, magnetic field is increasing, flux is increasing. When flux is increasing, according to Lenz's law, the current will get induced in such a way that it will try to decrease the flux. So who is the reason for flux to increase? It is the current. So if the current in this circuit after you close it is flowing in the clockwise direction, the induced current will be in such a way that it will try to decrease it. So the induced current in this scenario is supposed to be in the anti-clockwise direction. Am I clear with this point? Right. And let me repeat it. Listen to this carefully. When I close the switch, current is growing. So current is growing in the clockwise direction. The induced EMF should oppose the cause, means it should not allow the growth of current. It will try to decrease the growth of current. If that should happen, the induced current should be in the anti-clockwise direction. So that is why in this case, the induced current is in the leftward direction. Whereas if I take the next scenario, that is, I already have a switch which is closed. Now I'm going to open it. So when I say switch is closed, isn't the scenario going to be exactly the reverse of this? So at t is equal to 0, what has happened? The switch is closed. So when the switch is closed, the value of current is steady. When the value of current is steady, magnetic field is constant. When magnetic field is constant, flux is constant, except. So at some time t, what is going to happen after the switch is open? After the switch is open, current is going to be 0. When current is 0, magnetic field will be 0. When magnetic field is 0, flux is 0. So what is happening? The flux is actually having a higher value. From higher value, it is coming down to 0. So in the intermediate process, what is happening is the current is decreasing. Due to the decrease in current, magnetic field is decreasing. And due to the decrease in magnetic field, flux is decreasing. So there is a change in flux taking place with respect to time. Right? Here also EMF should get induced. Now I need to answer what is the cause for my decrease in flux. The cause for the decrease in flux is because the value of current is decreasing. So according to Lenz's law, what should happen? It will exactly try to do the opposite of what we are doing. We are actually trying to decrease the current. So the induced EMF will try to increase the current. If it has to increase the current, in this case, the induced current should be in the clockwise direction. Because the direction of original current can't be changed because the battery's direction is fixed. So the current supplied by the battery is still going to flow in the clockwise direction. But the induced current in this case will do what? That will also flow in the clockwise direction so that it can do whatever we are trying to, it can do the exact opposite of what we are trying to do. We are trying to decrease the current. It is saying, no, I'm not going to decrease the current. I'll increase the current. So it will come in support of the existing current. Right. So first point is we found the direction of induced current. If you know the induced current direction, we know that current can flow only if there is an EMF generated. There should be an EMF, right? So what is this EMF trying to do? This EMF is actually not supporting, it is opposing. That is why if you see, this EMF is called as opposing EMF, or you call it as self-induced EMF, or you also call it as back EMF. Are you clear with what is the statement? So you either call it as opposing EMF, or you call it as self-induced or back EMF. And this process, this is a phenomenon actually, which you can actually see. You saw it now, right? It happened for mutual induction, but it can happen for self also, right? So this is a phenomenon that can be observed. This kind of a phenomenon where there is a change in flux taking place in a coil and the EMF is getting induced in the same coil. That's what we call it as self-induction. Is the story clear? Are you all clear with this? Right. So with this, there are certain parameters that we need to study. But before that, make a note of this. So those who are online, could you understand?
Yes, sir.
Yes, sir.
Yeah. Are you done? So I'll explain, then you can copy. You have less time. So listen. So we understood that for self-induction to take place, the change in flux taking place through the same coil is responsible for the EMF to get induced. So having said that, can I frame a relation like this? The amount of flux that is associated with the coil is going to be directly proportional to the amount of current that is flowing through the coil. So this current is the one which is supplied by the battery, not the induced current. So N into phi, can I write it as directly proportional to I? So if I remove the proportionality symbol, I need to introduce a constant. And the constant that I'm going to introduce is what is called as L. And this L is what is called as inductance. So either call it as inductance or self-inductance also. Okay, you either call it as inductance or self-inductance. So from this, if you observe, L will be written as N into phi divided by I. So N into phi is measured in terms of Weber and I is measured in terms of ampere. This Weber per ampere is given a name called as Henry, and it is represented by the symbol capital H. Means inductance is a parameter, right, which is measured in terms of a unit called as Henry, but that Henry is obtained by using this Weber per ampere. Okay, like if you recollect, right, what we did in the case of a capacitor. In the case of a capacitor, we would have seen Coulomb per volt, which is called as Farad. In a similar way, here Weber per ampere is what is called as Henry. And secondly, when you deal with capacitors, right, mostly you would have seen in all the problems, the capacitance will be in terms of microfarad. In a similar way, when you talk about inductors, most of the inductors, the problems will be in terms of millihenry. Most of the problems. Okay. Now, this is one parameter which is called as inductance. I'll explain the significance of it. But we are also interested to find out what is the amount of induced EMF. See, this is known parameter. We know that the flux associated is going to be directly proportional to current. No doubt in that. But our interest is more about the EMF that is getting induced. Right. So when I say N into phi is equal to L into I, if I differentiate on both the sides, right? then I'll get N into d phi divided by dt is equal to L into di divided by dt, because here the induction is taking place only because of the change in current. The current is changing from 0 to some steady value, right? Due to the change in current only, there is an EMF induced, right? So, can I say this N into d phi by dt according to Faraday's law of EMI is going to be negative of E? So, can I say minus E is equal to L into di by dt, or EMF is equal to minus L into di by dt? Again, here the negative sign is an indication of Lenz's law. Now, if I take the magnitude of this, so EMF is equal to, if I take the magnitude of this, it is going to be L into di divided by dt. I'll put this in the modulus. Now, if I rearrange this equation, I'll get L is equal to E divided by di divided by dt. Am I right? Right. So now I have to answer a very important question. Listen to this carefully. I introduced something called as inductance, and we study something called as induction. Now I'm going to tell you a third term, which is called as an inductor. So what are the three terms? Induction, inductance, and inductor. Anything that ends with ION is a phenomenon. So induction is a phenomenon or a process. Anything that ends with ANCE is a property. For example, we have something called as resistance, capacitance. Those are all the properties of materials. So they are going to be the property of a material. Anything that ends with OR is going to be the device itself. Resistor, capacitor, inductor. These are all the devices. So they are going to be the devices. Am I clear with these points? Now, the most important question that needs to be answered is, if you say there is a device called as an inductor, inductor is something represented like this only, like a coil. Don't get confused, it's not a solenoid always. It is called as inductor, like how you put symbol like this for resistor and put R on top of it, you'll write something like this and put L on top of it. So every inductor has inductance or self-inductance associated with it. Now the question is, what does an inductor do? So for that, we will try to take some examples and then answer. If I ask you what does a resistor do, what will it do? Resistor will try to decrease the flow of current. Resistor will try to oppose the flow of current. What will a capacitor do? Capacitor will store charge in the form of energy. In a similar way, what does an inductor do? So most common answer is inductor will induce something or induce EMF. That's not its job. The inductor's job is observe. I'm going to take the similarity and then do it. If I write resistance in terms of voltage and current, can I write R is equal to V divided by I? So R and I, how are they proportional? They are inversely proportional in the sense resistor will oppose the flow of current. That is why they are inversely proportional. In a similar way, if I look at inductance and di by dt, it says that inductance is inversely proportional to di by dt. So what does an inductor do? The inductor will oppose the rate of change of current. The resistor will oppose the flow of current. Inductor will oppose the rate of change of current. It will not allow the current to change. That is why if you see it, it try to block AC. Because alternating current will try to change itself every time. So inductors will try to oppose AC more. They will allow DC to flow through it. So what do? They are going to oppose the rate of change of current. So that is the job of an inductor. If somebody asks you what does an inductor do, this is what you need to exactly tell. It will not allow the current to change with respect to time. Okay. So this is all about the self-inductance. Okay, these are all the mathematical parts, and the previous one was the theoretical part. I hope I'm clear, right? So make a note of it. Make a quick note. Are you done? Those are online. Are you done copying?
Yes, sir.
Okay. So any questions? Okay. Can you just take a screenshot? The time already we are 7 minutes late. You don't have phone? You have a phone? Can you just take a screenshot and send it to me?